Welcome to this revision video about natural changes and natural variations which can take place within the carbon cycle. We're going to start by considering one of the most important natural variations which can happen within the carbon cycle, and that is driven by natural changes to our climate. The diagram and graph on the screen shows you how the Earth's average temperature has changed over the last 800,000 years. And also how carbon dioxide concentrations in our atmosphere have also changed over that same time period. All of this data has been obtained from ice cores within Antarctica, so it's a very, very accurate record of what the temperature was like and what the composition of our atmosphere was like. We can see that the two lines on those graphs follow each other very, very closely. When temperatures are high, we can see that carbon dioxide levels are high. When temperatures are lower, we can also see that carbon dioxide temperatures are lower. And those two lines fit together almost perfectly. And that is because of this relationship, this very, very close relationship between carbon dioxide and temperature. And it is important to remember that this is a two-way relationship. So the amount of carbon dioxide in the air, that influences the temperature. Okay, we know how, for example, global warming is occurring as a result of increased amounts of carbon dioxide in the atmosphere. So where we have more carbon dioxide, we have warmer temperatures. Where we have less carbon dioxide, we have cooler temperatures. But it also works the other way, and there are processes and feedbacks that actually connect the temperature to influence the amount of carbon dioxide. So for example, as we'll see in a minute, when we have warmer temperatures, that can encourage more photosynthesis, which can actually cause the amount of carbon dioxide in the atmosphere to change. So this is a two-way relationship and is a very, very close link between these two things, between carbon dioxide and temperature. In order for us to understand these natural variations in our climate and the things that are driving the changes in temperature, it's important that we can understand how changes to the Earth's orbit can influence the amount of sunlight that's being received at the surface of the Earth. A famous astronomer known as Milutin Milankovitch, he discovered three subtle changes that take place within the Earth's orbit around the Sun, and how these changes over thousands and thousands of years very slowly influence the amount of sunlight being received. The first cycle that he identified, which we can see at the top here, this is known as the eccentricity cycle, and this basically explains how the Earth's orbit changes over time. So it changes from a relatively circular shape, like we can see at the bottom here, and over a period of about 100,000 years it stretches out to become a little bit more elliptical. It's a little bit more egg-shaped, if you like the example at the top. Where the Earth's orbit is more circular, the amount of time that the Earth spends close to or further away from the Sun is relatively even. So we tend not to have really, really cold winters or really, really warm summers. The difference between summer and winter is less pronounced. When the Earth's orbit is elliptical and it's a little bit more stretched out, the Earth actually spends more time further away from the Sun than it does closer to it. So the Earth's climate becomes a little bit more extreme, and in particular it causes winters to be very cold. Now that has further knock-on effects in terms of the formation of ice sheets, and ice sheets reflecting sunlight, driving the kind of onset of an ice age. But over this period of around 100,000 years, the Earth's orbit changes from being circular to elliptical, and then back again. And as it becomes more elliptical, the climate is becoming more extreme. The difference between summer and winter is becoming more pronounced. The second cycle is all to do with the obliquity of the Earth. And you'll notice that the Earth actually, when it spins around on its axis, it is tilted. So this cycle is all about the tilt of the Earth, and it varies only by about 2 or 3 degrees in terms of its angle. So this is a little bit more exaggerated in this diagram. Where the Earth is more upright, when we can see on the diagram on the right hand side here, where there's less of a tilt, there is less seasonal variation. So again, that difference between summer and winter is going to be less pronounced when the Earth is more upright. When it's more tilted, that difference is going to be greater. There is going to be more seasonal variation as a result of there being more of a tilt to the Earth. Again, this is going to influence how cold the winters are or how warm the summers are, particularly in the kind of far northern and southern hemisphere. The third one, which happens between about 19 and 23,000 years, is what's known as the precession of the equinoxes. And this is basically a little bit more simply summed up by thinking about the fact that the Earth wobbles on its axis. So we have a kind of stretching of the orbit, we have a tilt of the Earth on its axis, and also the Earth kind of wobbles a little bit like a spinning top. If you think about a child's toy, when you spin that toy round, as it slows down, that spinning top starts to wobble from side to side, and that's what's happening to the Earth over a very, very long period of time, so 20,000 years or so. What this does is, again, this changes the timings of the seasons. So as a result of the wobble, summers and winters could become longer or shorter and be occurring at different points throughout the lunar year. And that is a little bit strange, a little bit hard to get our head around, the fact that we think about summer as being a kind of defined period of 3 months, June, July and August, but actually that can change over much longer periods of time because of this wobbling on the axis. Ultimately, all of these variations in the orbit of the Earth, they are causing our climate to vary naturally over long periods of time. What this does then is it causes the Earth to swing between colder and warmer periods, what we call glacial and interglacial periods. So ice ages are made up of warmer and colder periods. So you could argue at the moment we are still in an ice age, we are just in one of these interglacial periods. During a cold period, a number of things will be happening to the carbon cycle. A number of the flows and transfers that move carbon around between the stores are going to change. One of those is going to be related to plant growth and photosynthesis. So as temperatures drop, plants are going to photosynthesize less because that plant growth is going to be restricted, and that's going to reduce the amount of carbon dioxide that they're going to absorb. Alternatively though, as the oceans get colder, they can actually absorb more CO2 from the atmosphere. The colder the oceans are, the easier it is for them to absorb carbon. So actually we've got kind of a bit of a counterbalance going on here, whereby although there's less CO2 being absorbed in the atmosphere, more CO2 is being absorbed by the ocean. So this is a very complex balance between the different stores. On the other hand, within the ocean, as the ocean temperatures get colder, any marine organisms living within the ocean, plankton for example, that photosynthesize, just like the plants on the land don't photosynthesize as readily when the temperatures are colder, the same happens in the oceans. So the oceans might absorb more carbon dioxide directly from the atmosphere, but organisms within the ocean might actually photosynthesize less. Another thing that can happen if sea ice cover increases, which it would do during a glacial period, the Earth's temperatures would be colder and sea ice would be much, much more extensive across parts of our oceans. That basically prevents the release of carbon dioxide from the ocean. It's a bit like having a lid on top of the ocean, and it prevents that carbon dioxide from diffusing out into the atmosphere. The sea ice also prevents the growth of algae, which, as we've said before, is a photosynthesizing organism. So that algae and that plankton, that can't photosynthesize, and therefore it's going to absorb less carbon dioxide from the atmosphere. On the other hand, when temperatures are warmer, such as in an interglacial period, the opposite of those processes are going to happen. So, for example, warmer temperatures are going to encourage plant growth, and it will increase the amount of CO2 being absorbed. The warmer oceans are going to absorb less CO2 from the atmosphere. So the opposite of all of these processes is true during these interglacial periods. Another couple of important points to be aware of, though, during these interglacials or these warmer periods, one of those is to do with permafrost. So permafrost is the permanently frozen ground that we find extensively across Canada and northern Russia. Where that soil is frozen, the carbon, particularly in the form of carbon dioxide and methane, is locked away within that frozen ground. But as it starts to melt, that carbon is released into the atmosphere. The other thing that can happen as well as the temperatures warm, areas can also become drier. And because water is a limiting factor on the rate of photosynthesis, as in without water plants can't photosynthesize, if areas become drier, that can also cause plant growth to slow down, and that can influence the uptake of CO2. So there are a very, very complex system of changes happening here. Some things causing more carbon dioxide to be absorbed, other things causing less carbon dioxide to be absorbed. And we can start to see here how that link between temperature and carbon dioxide is so close and so intertwined, because when one thing changes, the other changes as well. Another important natural phenomenon influencing the carbon cycle is that of volcanic eruptions. We know from the work that we've done about the processes operating within the carbon cycle that volcanic activity is responsible for returning carbon to the atmosphere, particularly after rock has been subducted at a destructive plate boundary. The rock heats up, the carbon dioxide is released in the form of eruptions. And volcanoes emit, depending on the amount and size of eruptions in any given year, between about 130 and 380 million tonnes of CO2 every year. Now, while that might sound a lot, in comparison, human activity releases over 30 billion tonnes, which is 100 to 300 times more carbon dioxide. So we can think about volcanic activity being equivalent to maybe only 1% of human emissions. However, when they do erupt, volcanoes can have a significant impact, but not in the way that we might obviously assume. So we're right in saying that carbon that's stored within the lithosphere does get released during volcanic eruptions, and most of that is being released into the atmosphere in the form of carbon dioxide. But the amount actually being released doesn't go on to impact our climate significantly in the terms of kind of causing any noticeable warming to our climate. The bigger influence that volcanic eruptions have is that large volcanic eruptions can actually cause a cooling effect. That's because all of the tiny particles of ash and sulfur dioxide in particular that are being emitted from this volcano, if we imagine all of these little particles within this ash cloud, when they get really, really high up into the atmosphere, what they are doing is effectively acting like tiny mirrors to scatter and reflect sunlight that is coming in from the sun. That actually then leads to a cooling effect, and some large eruptions have had significant cooling effects on the planet. So in 1991, Mount Pinatubo in the Philippines, that had one of the biggest eruptions that we've seen on the planet for quite a number of years, over 100 years. In terms of its explosivity, we use the scale, the VEI, to represent the explosivity of an eruption. Pinatubo was a 6 out of 8 on the VEI, so a very explosive eruption. And that eruption actually caused global temperatures, so not just locally, but global temperatures to drop by 1 degrees C across the whole planet the following year. So that single eruption emitted enough aerosols to reduce global temperature by 1 degree C. Now, to put that 1 degree C in context, all of the human activity that has emitted carbon dioxide since the Industrial Revolution, that has caused temperature to go up by 1 degree C. So these single events can have significant impacts, but their impacts tend to be cooling rather than warming. Wildfires and the combustion of biomass, that's another natural phenomenon. Although they can be started by human activity, wildfires are a natural part of the carbon cycle, and every year about 3 to 4 million square kilometres burn, which contributes around 8 billion tonnes of CO2. Now again, if we compare that to the 30 billion plus tonnes of CO2 that human activity releases, we're not talking about wildfires being on the same sort of scale as the combustion of fossil fuels. However, that amount of carbon is still a significant transfer within the carbon cycle. So when trees are burnt or vegetation catches fire, that carbon from the vegetation, from the biomass and from the soil is rapidly transferred to the atmosphere. Although plants, when they burn, they don't release all of that carbon. It only releases maybe 10 to 20% of all the carbon that is stored within a tree or within the forest, but that's still returned to the atmosphere relatively quickly. We also have a sort of secondary impact by the loss of that vegetation reducing the amount of photosynthesis that then takes place, because if the trees are dead or they've been burnt, they're not going to be photosynthesizing. What does happen though in the long term is that fire can stimulate new growth by clearing out old diseased vegetation, opening up areas of the forest floor, returning nutrients from the ash into the soil. All of those things can encourage plants to grow, and when plants are young and growing quickly, they absorb lots of carbon. So in the long term, wildfires have actually reached a little bit of what we would call a dynamic equilibrium, whereby the carbon that is emitted by a fire is then subsequently reabsorbed by the new plant growth that is stimulated as a result of that fire. However, this neutral effect that we could argue wildfires have on the carbon cycle, this neutral effect is being eliminated, because actually as a result of human activity, wildfires are becoming more frequent, and when they happen they're becoming more intense. So even though in the past it was always assumed that wildfires actually had a kind of neutral effect on the carbon cycle, that is actually changing as a result of human activity. So in summary then, our climate fluctuates naturally, and those climate fluctuations are driven by long-term changes in the Earth's orbit, known as Milankovitch cycles. And that brings us these glacial and interglacial periods that we experience relatively regularly throughout Earth's history. The glacial and interglacial periods themselves then drive changes in the carbon cycle, particularly things like rates of photosynthesis, Glacial and interglacial periods themselves then drive changes in the carbon cycle, especially things like the rate of photosynthesis, which goes up when temperatures are warmer or goes down when temperatures are colder, and also the exchange of carbon dioxide between the ocean and the atmosphere. And all of those things are influencing the temperature. Volcanic activity, while is a natural process and does impact the carbon cycle, that impact is very limited. And certainly in the short term, those carbon stores are not changing significantly. It's also worth remembering that large eruptions are much more likely to have a cooling effect than they are to have a warming effect. Wildfires have also historically had a neutral impact on the carbon stores. The amount of carbon released by a fire was very much offset by the new growth stimulated by that fire. However, that neutral balance is actually changing as the frequency and intensity of fires changes as a response to global warming.